All right, so we got a little bit of last minute stuff, things to finish out our integration time, the end of the semester. They're cool topics. So it should relate to what we've done already, but it adds a couple nuances. So let's talk about the things that we've learned. There are definite integrals, integrals from some A to some B, which is area between the x-axis and the curve. We call it area under the curve, but it really is a loaded term under. It's between the x-axis and curve. Now, what we're going to do now, though, is instead of giving the upper bound some fixed amount, let's say we have an interval that starts at a, but we don't know where it stops, that'd give us this integral from, a to x, like that f of x, where we'd try and figure out what the area is, and we can figure this out. We'd represent, so this is like the antiderivative whenever you're doing the integral of little f of x, like this. We'd say the antiderivative is big ol' f, and then what that means is if we took the derivative of big ol' f, capital F, then you'd get little f back. So there's just one's the derivative of the other, and so that big F right there is the antiderivative. We'd find that by doing from the situation right here. Then if I anti-derived, it would be big ol' f of x minus big ol' f of a. Why don't I just bring that down with it? So we're just talking about that big ol' f. I'm going to delete this out of here because I actually want to write what was supposed to be in there. Make my eraser a wee bit bigger. There you go. Make it somewhat functional. But this is the integral from some number to x. It's a little f inside, which gives big ol' f of x, and more specifically, if you have these bounds on it, you put the upper bound in first and then the lower bound in. And it just means having an x in there at first. And that's okay. We're just waiting to put in a number. You just tell us what the numbers are. So on the next thing is we're going to do this from 0 to x and just show you how this plays out in a drawing of f right over here. This is a graph of f. Okay, so we're going to use that to our context. And then this is the lower bound of 0, upper bound of x. And then, but the way I'm going to do x is there's a table that says, what if x is 0? What if x is 1, 2, 3, and so on? What would the represented area under the curve, which again is area between the x-axis and the curve for that particular x? So for the first one, if I put in 0, so it really means, I'm going to write really tiny underneath here, that would be the integral from 0 to 0. And that didn't work out. 0 to 0 of f of x dx, like that. And that's always going to be 0. So whenever these bounds match, when the top and bottom bound, it's not that there's a 0 involved in it. It's that there's no width to the interval. The lower bound and the upper bound are the same thing. That's always going to give you a result of 0. And then the next one, let's just change up the color every other one so that you can kind of see a contrast here. We'll go pink, blue, pink, blue. And this would be 0 to 1. So remember, this is an x. I'm changing the upper bound each time, and that would be f of x. And where do I get this? What does that represent? Remember, that means the area under f of x, or between the x-axis and the curve. And we have f of x over here. So it would mean the region. Let me get out my proper blue right here. This. So that would be the area between the x-axis and the curve from 0 to 1. And we need to find a way to get that. I'm going to count it by rectangles. So if I just grab my little pointer here, that's 1, 2, like it's square units, 1 by 1 square. So 1, 2.5. So the area is actually 2.5. That's pretty fun. So grab that. So 2.5. And then we'll go to 2. Maybe I'll go green on the next one. That looks like a good color. Going green. And that little integral bit from 0 to 2. F of x dx. When you go from 0 to 2, you go over to the picture, and you can get that result by shade in that same color. That's just adding both of these together from 0 all the way to 2 now. Then you could add a little bit more to it. So if I'm counting like I did before, it's the 1, 2, 3 whole squares, and then 2 halves. So 1, 2, 3, 4 is the total area on that one. So that'd be 4 total. So again, remember an integral, the symbol with that integral, that squiggly S line is the area beneath or from the x-axis to the curve. And f of x is just the name of the graph f. If it were g, then we do the area under g. And then the upper bound, we're just changing it every time. So we left The upper bound is x, which means I can put in any value that I want, and it allows it to vary. It's actually giving me, for each value of x, I'm getting a different area. So it seems like the further I go over, the bigger the area gets. And that makes sense because we're kind of like accumulating more and more stuff the further we go along. And then we throw back, we can go back to pink, right? We've been doing this for a little while. So 0 to 3, I think you get the idea of f of x. Got to go over to the picture, see what that means. So if I shade until we get there, adds one more. So the previous one was 4, and I'm adding another one that's 5 total. If you want to just count it up, you can. And then going 0 to 4, 1, 2, 3, 4. Let's see where that takes us. Let's go that light blue again. Integral 0 to 4 f of x dx. And let's see what the slim shade says. Here goes. Shade, 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 shade. Adds another half. So now we're at 5.5 total. So we're just accumulating as we go along. And that's actually some way to think about this. It's just an accumulation of areas from 0 to x. And then when we go to 5.5, though, look what happens when you jump to that next one. That 5.5, what it does is it adds this area underneath here to what we already have as 5.5. So it actually, let's just take it on here. I already know that's going to end up being 5, just plain old 5. Because remember, we had as 5 before, but then we put this negative. Any area that's below the x-axis then is, in an integral, that means the net of it is negative. Its accumulation is negative. Now, you guys did the lab with the inhaling and exhaling, and that makes sense. If this is a rate of change curve, the area under rate of change gives you total change. And what we had in the lab was liters per minute or liters per second. And you would inhale and breathe in so much air, and then underneath the axis was the demonstration of exhaling, removing the air that you took in. So these are the values that go inside here. This is called an accumulation. I guess we could call it a definite integral. But I think the word that was going for, remember, I'm borrowing this whenever I borrow things that have fill in the blanks. I have the worst time, but it's actually kind of fun. Sometimes I put in whatever I want. Accumulation sounds like the word I'm looking for. Then there's this, the fundamental theorem of calculus. But remember we already said the fundamental theorem of calculus was this like area thing? Well, it's kind of considered part 2. So we give part 1 and part 2. So the folks who know a little calculus, they go, oh, fundamental theorem. And if you bring it up at, at a party or something where you'd normally bring it up, and somebody said, at relays over at Peggy's or something, and they're going to say, yeah, which part? Do you mean part 1 or part 2 of fundamental theorem? I dare you, just try it out this week and just ask somebody, just mention fundamental theorem of calculus, and I bet they say which one, part 1 or part 2. Okay. So this next chunk is related to that. So what happens is this looks like it's related, but it also has a really cool property to it. So I'm going to focus on the cool property of it. Do you remember how integrals are the inverse of derivatives? So what happens in this very, very key setting, if this is a constant, this is important at the bottom, just like we did for our accumulation, and this is just x, so up top here, and you get an integral and a derivative, what we're going to find out is that this cancels with the derivative of the integral, quite literally cancels. And I'm going to show you this once, and then I'm going to delete it and then show you the long way, right? That's my job. I get paid big bucks to show you the long, hard way to do things. But the idea is the derivative and the integral cancel, and I am just going to get f of x. Now, you might think that little a disappeared, like what happened to the a, the constant there. It kind of does disappear. But this is where I'm going to arrive when I'm done, and that's what I'm going to write again here in a little bit. But I need to show you where that comes from and why that I'm just f of x. It's the fact, the second fundamental theorem is that derivatives and integrals are inverses, and they cancel each other. It's a huge deal. It makes a big difference in the world of, making rockets fly and, whatever necessary calculus applications are out there. Keeping your plane in the air. It's kind of nice to have that, at least I think anyway. So let's do this. So here's the long way to explain that this, what you see before your eyes, is just f of x. If I antiderive it, remember it's big ol' F, and I keep the derivative in there, like what I'm doing is I'm deriving this thing I know how to do, which is antiderive. And so I'm going to put the derivative of the antiderivative, which would be big O, the antiderivative with the upper bound plugged in minus the antiderivative with the lower bound plugged in. Okay, so this is, I wrote it up above too, whenever you see this, the antiderivative of f of x is usually symbolized by a big capital F, and then you put the upper bound in, and then you put the lower bound into the antiderivative, and you subtract them. It was on the quiz. So that's the idea. Well, now if I derive both of those, so I come in with a derivative, I always do the same to both sides. d dx. Okay, what happens is derivative of big ol' f of x is actually just f of x. They cancel each other. That's actually one of the definitions. So if you just integrated and got capital F, then if you derive, you're going to take you right back. So you integrated and got capital F, and now you're going to derive, and it would take you back, right? We're just doing and undoing. Sounds silly. But when I put it all together, you're going to love it. So that's my integrate and derive. And then if I go and derive the integral on the right-hand side, that piece that you're looking at right now, that's what I'm doing, the big ol' f, I'm just going to get little f, so that's what I wrote. And I also have to derive the minus f of a. Well, f of a is some constant. When you put a number inside a function, you get out a number. And so that's just going to be 0. Okay, so this is a constant. Whenever you put a number in a function, you get out a constant. And you guys know the derivative of a constant is always 0. Okay, so what happened is when I did this and I took the integral of f of x dx, like I actually did it, see that blue part here, big F of x minus big F of a, that's the integral. That's how you do the fundamental theorem, first fundamental theorem. And then I brought in this pink derivative, do it to both sides. You're noticing that the pink derivative just cancels the integral, and I'm just going to get f of x. Because when I do it on the right side, when I take the derivative of capital F, it just gives me little f. That's its definition. Okay, so big F is the antiderivative of little f, and so the derivative of big F gives you little f. And then over here, this is a number, and the derivative, when you derive something that's added or subtracted, you have to derive both terms, kind of like when we had, back in the old days, derivative of x squared minus 5x would be, 2x minus 5. You have to derive both of these, and the derivative of this constant is 0. So this is the long way of me showing when I derive this thing, I'm going to do it nice and formal like. I just get the derivative of big F of x is just little f of x. And the derivative of the constant that you get from putting a number, into the function is 0. The derivative of any number is 0. So it's just ol' f of x. So the long and short is we're going to memorize this crazy thing. We're always going to see the derivative of any constant, doesn't matter what it is, to x. Of f of, and it's always got t in here, and the reason that is so you don't confuse this upper bound x with the integrands input variables while you're doing this process. So it's pretty common to see it like this. And then you'll notice that these guys cancel. And the only thing that's wild that you have to remember is that it cancels the integral, but this variable ends up being substituted into the function. Okay, so I'll give you another example here in a minute. So an aside, an example, extra examples, we'll call it. Right there. So if I do this from, I'm putting a number in here like 3 to, I'm going to put w, f of t, dt. The integral and derivative, I'm going to come in here with my derivative. If you come along and derive, you're going to find out the derivative is going to have the same variable as the upper bound. It's usually x, but just giving you fun things to think about. And when you do derive an integral, it will cancel the integral, and you're left with just f with w placed inside. Okay, and you might be saying, what happened to that 3? Well, it was there, but if I put that, let's say I put 3 into the one that I just did earlier, if this is ever 3, when I go and derive f of 3, that's just deriving a number, and I end up getting this plus 0 at the end. So that's why we don't, that lower constant, no matter what it is, gets plugged into the antiderivative, and that produces a number. And when we derive numbers, we get out 0. Okay, so these are, back that up. I don't need that on my screen. There. That's the big to-do, and we'll practice here in a second, but derivatives cancel integrals in a very specific way. I want to put in here, I actually know the blanks, derivatives and integrals are inverses. Muy importante, and then they cancel each other out, just like multiplication and division. In example 1, the graph of f is derivative of big ol' F, capital F. So capital F of x is considered the antiderivative. F of x. Okay. Now, variations of the fundamental theorem of calculus. I'm going to just pause, and we'll probably not address in Math 50. But if you keep going, Math 70 will take it on and beyond. It's not much different, but it's enough different that I just want to kind of steer away from it from now. Okay, let's keep rolling. So let's see this in action. So I'm not saying it's the same process, but in a different way. It's saying find f prime of x, by the way, which would be little f of x. So the derivative of big capital F is always going to be little f. And my handwriting is not helping this at all. So what it says for me is I'm going to go get wee little f prime of x, which means derive big F. Oh my goodness. Got this. Big F. There we go. Of x. And to get f prime of x, that means I have to derive both sides. So I need to go derive this whole thing from 2 to x. Notice, see how that variable x doesn't match the function inside has t's, just to keep it from mixing up those variables. It's a common practice in this fundamental theorem type of question. So you'll even, that might be a way to recognize it too, like, oh, the integral has t's and there's x's in the rest of it. Ta-da, that's probably this fundamental theorem thing. So when I derive, you want to think of it cancels, but then you also have to substitute that x in and replace the t's, because it actually happens when you're doing this process. You're actually subbing in the x and it replaces those. And so ultimately f, big ol' F, capital F, f prime of x is going to be 3x squared plus 4x. And you're going to say, isn't that just, I always get the same thing when I'm done? Well, it's because I'm deriving both sides, but you also don't forget you are subbing in the x, and those t's get replaced. But yeah, when you derive an integral, it cancels that integral symbol. Gone. Next one over. Here is big ol' f prime of x, means I need to derive what I got up above, which is this pi over 2 to x cubed. Now this is a little bit of a variation. I think I'm going to be okay with showing you. Okay. Or maybe I'm not. I don't know. I'm trying to decide if I want to go that far into it. Yeah, maybe not. How about this? It's not going to show up in your near future, but what happens is when you do the derivative, if there is a chain rule involved, so the inner piece, this thing when I drop it down here, I am taking a derivative, but whenever you take a derivative of something with an inner function, you have to do the chain rule. And I've been doing the chain rule, you just didn't know that. I've been deriving x when you put it in there and then take but the derivative of x is just 1. So we've been kind of ignoring that fact. So again, this is just extra bonus FYI, the kind of thing that sometimes you guys might want to plug your ears if you're already full at this moment. But check this out. I'm taking the derivative of both sides because the directions said find f prime and I have f. So I'm deriving both sides, do the same to both sides. I will get just plain old sine because it just cancels. Now notice I'm not like deriving sine and writing down cosine. And I didn't do that on the others either. I didn't do it on the previous one. I didn't take the derivative of 3t squared plus 4t because the derivative, when I took the derivative of the integral, it just canceled the integral, so I never had to. It annihilated it. There's no need to perform any type of power rule or anything on this. So when you derive something that has an integral in front of it, the only effect is it will be canceling that integral out. And there's no longer a d dx, it's gone, so you're just left with the function as it is. And that's the beauty of this process, is realizing, oh, it just cancels the integral. I don't actually have to do anything to that function. So keep that in mind. And I usually just drop what the upper bound is. Yep, just did it. So you always drop it in there. And it's been x up to this point, and I would stop. However, when you're deriving with something with a more complicated inside, you have to use the chain rule. So the chain rule is an important part about this. I have been doing it all along, even with like this one. I put x in here, but what I would have to follow with is times the derivative of x, which is 1 on the previous ones. But times 1 is negligible, so it doesn't change the effect of it. But this one definitely needed that chain rule. That's the next complication we can do with this fundamental theorem. If the upper function is something other than x, you need to take the derivative of that immediately thereafter. Okay, let's stick with the kind of more straightforward one down here. We kind of see it multiple times. So these are quick. I'm going to do a little zip through. So ready? F prime of x in this one. Take the derivative. Told me to. And when you do that, you're deriving both sides. I'm taking the derivative here. And here it makes it f prime. Ka-chow. On the right, got this cancellation going on, and I just get x cubed. And you're saying, wait, don't I take the derivative of that right after? Yep. But it's just 1. So we'll leave it off. F prime of x is just x cubed. Now, this one had a lower constant of 2. This next one has a lower constant of 0. It doesn't matter what the constant is. The derivative will be the same either way. So check it out. So I'm going to come in here, and I'm going to derive both sides. Derive both sides. That's how I get f prime here. So that causes f prime of x. And the derivative here cancels, and I just get 5. It just cancels the integral. You're like, wait, I usually put 5. I like sub it in here. You sub it into any t that you have in the integrand. I don't have one, so it's just 5. Okay, so it's a fun little nuance. Next one. The constant is -1 at the bottom, but that doesn't matter. I'm going to derive both sides. So d dx. Get f prime of x. Cancels here. And I'm left with 4x minus x squared times the derivative of whatever I just subbed in there, but it's just 1. That one's done. So I hope you're feeling a little bit of the rhythm that goes with this. Next one, there's a pi. That's a number. That's when I derive. But that constant hasn't mattered, has it? So it cancels. F prime of x is now just cosine of x. Continuing. And this one's the one that's, again, plug your ears if you're just kind of hanging on by a thread, but this one's got a little more complicated upper function, but you can handle this, right? I get f prime of x. This cancels. I sub this in. What happens is it's x squared cubed. I just drop it in there, but times 2x. You always have to put the derivative of the upper bound of the integrand. You have to put that afterwards. The chain rule. When you're deriving a function with an inner function, you must do the chain rule. And let's do maybe one more inside here. Yep, let's do one more. Let's go to number 9. Yeah, actually, I'll stop there. I think that's pretty good. So next round, I'm going to get into some other details totally related, but also we're going to talk about areas and just a nuance of multiplying, having a multiplier in front, little changes, like they're actually little graphical shifts, and we'll talk about the properties related to that.